Today I'm going to make some of this ordinary paint stripper into a super useful chemical called benzaldehyde. If you've never heard of benzaldehyde, it's basically just a benzene ring containing a single formyl group, making it the simplest possible aromatic aldehyde. It smells a lot like cherries, and despite being basically composed of incredibly carcinogenic benzene and formaldehyde, benzaldehyde itself is fairly non-toxic and widely used as a flavorant in cherry sodas. Benzaldehyde is also widely used in organic synthesis, where it undergoes aldol condensations to form cinnamaldehyde or styrene derivatives. It can also condense with itself to form benzoin, or with dimethylaniline to form malachite green dye. Cyanide will react with benzaldehyde to produce mandelic acid, while nitroalkanes will react with benzaldehyde to produce phenyl nitroalkenes. These are all incredibly important reagents in further synthesis, and that said, benzaldehyde can be used to make a wide array of useful dyes and pharmaceuticals. I plan to make videos on several of these in the coming weeks and months, but before I could do that, I needed to make the benzaldehyde itself. This is something I'd wanted to do for a really long time, but I kept putting it off since virtually every method I came across seemed to require either excessively difficult to get starting materials or produce comically low yields. At a certain point, I figured I'd settle on the classic Adduct reaction, as it seemed to be the best option with what I had available to me. However, this method had two major problems. Number one is that the Adduct reaction uses the incredibly toxic volatile carcinogen chromyl chloride as an oxidizer, which I wanted to avoid if at all possible. Number two is that despite me thinking this was a classic organic synthesis, I really couldn't find any concrete procedures or videos online of this being done. I was within a few hours of just winging it as usual, but then I was informed that Nile Red had actually done the Adduct reaction before in a somewhat recent video to make some DIY cherry soda. I figured I'd at least give it a quick look to see what kind of misery was in store for me, and after seeing the massive volume of liquid carcinogen that I'd need to produce in order to make a tiny volume of benzaldehyde, I decided to go back to the drawing board. Later that same day, almost by chance, I came across an old patent on converting alkyl-substituted aromatics to their respective aldehydes or ketones using persulfate salts as an oxidizer. I was pretty skeptical at first, given that persulfate seemed like an extremely strong oxidizer for making such a delicate molecule, but when I saw the reported yield of 95%, I decided I had to give it a try. To get started, I began by adding a half gram of ferrous sulfate heptahydrate and 1 gram of copper acetate to a 2-neck round bottom boiling flask, followed by 100 milliliters of a 20% ethanol solution. The iron sulfate is going to be the key oxidation catalyst here and can be substituted with other iron salts or silver nitrate. The copper acetate, on the other hand, is technically not required, but it is highly recommended as it works effectively to inhibit various side reactions, particularly the dimerization of the benzaldehyde to benzoin. The ethanol is also technically optional, but used to help increase contact between the organic and aqueous layers during the reaction. Anyway, after allowing this to mix for a few seconds, I next added 50 grams of toluene paint stripper and allowed this all to continue mixing for a few minutes. Meanwhile, I next dissolved 280 grams of sodium persulfate in a minimal volume of water, and this represents a little more than twice the molar equivalent of the toluene. This might seem like a lot, but this huge mass of salt is necessary to fully oxidize the toluene to benzaldehyde. Once the sodium persulfate was done dissolving, I set the boiling flask up with an addition funnel and a thermometer. The thermometer was set to monitor the reaction temperature, and the addition funnel was filled with the saturated sodium persulfate mixture. I next transferred all of this to a heating mantle, heated the mixture to around 75 degrees Celsius, and then slowly opened the stopcock to add the sodium persulfate to the reaction mixture dropwise. Now, because I'm trying to get water-soluble sodium persulfate to react with water-insoluble toluene, extremely aggressive stirring is absolutely necessary here. And I quickly realized that the weak stirring function on my heating mantle was simply not going to cut it. To try and fix this, I decided to quickly cut the heat and move the boiling flask to my hot plate to continue the reaction. The stirring on my hot plate is way stronger than my heating mantle, and at this point you really don't need to apply that much heat anyway. To that end, at this point all I really needed to do was continue to slowly add the sodium persulfate mixture dropwise under very strong stirring while maintaining a temperature between 65 and 80 degrees Celsius. This ended up taking quite a while given the massive volume of persulfate, so while this is playing out, I'll do my best to try and explain what's going on here. If you take a look at our starting reagent toluene, you can see that the molecule is basically just benzene with a single methyl substituent. The hydrogens bound to this methyl side chain are particularly reactive, and this is due to the stability of the benzoic radical ion formed after the hydrogen atom is abstracted. And this is because the intermediate is resonance stabilized by the pi system of the adjacent aromatic ring. As a result, the carbon of toluene's methyl group is more susceptible to oxidation than the aromatic carbons. Now, I haven't been able to find any mechanism for this reaction, but I assume it begins with a nucleophilic attack by the methyl carbon on the peroxide oxygen of the peroxodisulfate ion to give an intermediate sulfate group. This sulfate group would then be quickly hydrolyzed to a hydroxyl group forming benzyl alcohol. Now, while I am fairly confident that this is the first step of the oxidation, I really don't have any idea how the second step goes. Let me know in the comments if you do know how this would work, but most of the time the oxidation of hydroxyl oxygens to carbonyl oxygens are just glorified E2 reactions where the oxidizer replaces the OH bond with an OLG bond where the LG is a good leaving group. I don't really see how the peroxodisulfate radical could do this alone, so I'm assuming this is where the iron catalyst comes in. Since at this point I'm starting to get bogged down on the mechanism while writing the script, let's look at this a different way. If you calculate the oxidation state of toluene's methyl carbon, you can see that it's in its least oxidized electron-rich -3 state. Looking now at persulfate, you can see that the two peroxide oxygens are in the -1 state. Since oxygen is most stable in its -2 state, this whole thing is begging for more electrons, which it'll steal from the methyl carbon. This will result in two stable sulfate molecules and benzyl alcohol, where the methyl carbon is now in the -1 state. When this happens again with the second persulfate, the methyl carbon is now in the +1 state, resulting in benzaldehyde. A third oxidation would put this carbon in the +3 state and create benzoic acid, which can be easily afforded by oxidation with permanganate or chromium trioxide. This is why two equivalents of persulfate are required for each equivalent of toluene, as using molar equivalents would simply produce benzyl alcohol. On that note though, this procedure could definitely be modified as an easy way to produce benzyl alcohol, and if you happen to already have benzyl alcohol, it could be used as a starting point here rather than the toluene. This would require half as much persulfate, and you could probably eliminate the ethanol altogether if you went this route. Anyway, with my best attempt at the theory out of the way, let's look back at the reaction here. As you can see here, the mixture did darken somewhat as the reaction went on. I'm not really sure whether this is a feature of the reaction or a result of my very inconsistent temperature control. I did find that the ideal temperature for this reaction is right around 70 degrees Celsius, and heating closer to 80 degrees Celsius caused the ethanol to start rapidly boiling away, along with the formation of this brown polymerized crap that stuck to the sides of the glass. You'll also notice here that at a certain point I completely removed the boiling flask from my hot plate and transferred it to a stir plate. The reason I did this is because once around half of the persulfate had been added, the reaction became a lot more obviously exothermic, and this is why I accidentally let the temperature go too high a few times. However, this does have a benefit because at this point it's not really necessary to apply heat to the flask at all, as the heat created by the reaction itself easily maintains the temperature at 70 degrees Celsius. Anyway, once all of the persulfate solution was added, I allowed the mixture to continue reacting for another 15 minutes before I cut the stirring and allowed it to cool. I then transferred all of this to a 1 liter separatory funnel, at which point I was hit by an overwhelming cherry smell. This was pleasant at first, but I promise you it got really old really fast. Anyway, I next drained away the lower aqueous layer, set it aside, and then collected the upper organic layer containing my benzaldehyde. I then rinsed my reaction flask with ethyl acetate to remove any residual benzaldehyde, and then added this to the separatory funnel along with my earlier aqueous layer. This was then rinsed 2 more times thoroughly with 50 milliliter portions of ethyl acetate to extract all the residual benzaldehyde, with the organic layers being combined with the original extract each time. I then returned the combined organic extracts to the separatory funnel and rinsed them once with distilled water and twice with saturated sodium chloride. At this point, I was left with a wet mixture of benzaldehyde, unreacted toluene, benzyl alcohol, ethyl acetate, and some unknown reaction byproducts. I decided first to add a few grams of anhydrous magnesium sulfate to the mixture to pull out any residual water, and my plan from here was to try and purify my crude benzaldehyde by distillation. To this end, once I felt the magnesium sulfate had enough time to pull out all the water, I went ahead and filtered the mixture directly into a boiling flask. I then set it up for a short path distillation and began distilling the mixture. My idea here was that the ethyl acetate should distill off first around 77 C, and then only once all of it had boiled away, the temperature would spike to 110 C where the unreacted toluene would distill off. This would be followed by a second spike to 178 C, at which point pure benzaldehyde would begin distilling. However, what really happened is that while the initial distillate was indeed nearly pure ethyl acetate, the temperature of the distillate didn't hold at the boiling point of ethyl acetate. Instead, it slowly crept up to a point somewhere between the boiling points of ethyl acetate and benzaldehyde, where it became clear that I was distilling a mixture of benzaldehyde, ethyl acetate, and probably unreacted toluene. With that said, I think something with a lower boiling point like diethyl ether would have been a better extraction solvent than ethyl acetate, but sadly, I'd used up most of my ether a week earlier on a different project. At this point, I feel like I probably should have just continued the distillation to remove all of the brown discoloration, but in my moment of panic that things weren't going like I expected them to, I instead cut the heat and pivoted to an entirely different workup. For my backup plan, I began by mixing up a saturated solution of sodium bisulfate by adding sodium metabisulfite to around 200 milliliters of water until no more would dissolve. I then began to slowly add my crude benzaldehyde, which quickly caused the mixture to become somewhat cloudy. What was happening here is that aldehydes will form an adduct with sulfite, and the benzaldehyde sulfite adduct in particular is insoluble in the presence of excess sulfite as well as in organic solvents. My new idea was to collect this insoluble adduct, rinse it thoroughly of all impurities, and then break it back down to hopefully pure benzaldehyde. To that end, I went ahead and added all of my crude benzaldehyde along with my distillate from the last step, and allowed it to all continue reacting under strong stirring for another 30 minutes. I also added a few extra scoops of sodium metabisulfite to assure that sulfite was present in a large excess. After 30 minutes had passed, I was left with a mostly uniform slurry, and the cherry smell had completely disappeared. I then passed this all through my Buchner funnel to collect the insoluble benzaldehyde adduct, rinsed it thoroughly with both ethanol and acetone, and then transferred the paste to a petri dish to dry. Here you can see the filtrates from the initial filtration as well as the ethanol acetone rinsing. The upper layer in the flask on the right hopefully contains the ethyl acetate along with the unreacted toluene, while the flask on the left should contain all the other water-insoluble impurities in the crude benzaldehyde. Anyway, after a couple days, my benzaldehyde sulfite adduct was now totally dry, and so I went ahead and weighed it for a final mass of right around 60 grams. Allowing it to dry completely like this really wasn't necessary, and if anything, it might have made the next step take a lot longer than it would have otherwise. For this next step, I simply added a saturated mixture of sodium carbonate to a separatory funnel, followed by about half of the benzaldehyde sulfite adduct. This was then aggressively shaken and then allowed to rest briefly before giving it another good shake. What's happening here is that in the presence of a base, the benzaldehyde sulfite adduct will break apart into benzaldehyde and the respective alkali sulfite. As the reaction proceeds, an upper layer of benzaldehyde will start to form along with the return of the overpowering cherry smell. This whole process did take a lot longer than I expected, and I think it would have gone a lot quicker if I had done this while the adduct was still wet. Regardless, after a lot of shaking and the addition of a bit more sodium carbonate, eventually the adduct had been completely broken down and liberated all of the benzaldehyde. I then went ahead and allowed the layers to separate, drained off the lower aqueous layer, and collected my upper benzaldehyde layer in a small flask. I then rinsed the aqueous layer once with most of what little diethyl ether I had left, and combined this organic layer with my benzaldehyde extract. Now at this point I had a flask containing mostly wet benzaldehyde along with a little bit of ether and whatever is responsible for this stubborn orange discoloration. To try and clean this up, I began by drying off the excess water with more anhydrous magnesium sulfate and then removing the wet magnesium sulfate by passing the mixture through my Buchner funnel. I then added about a gram of activated carbon to the filtrate and shook the flask aggressively to try and remove some of the discoloration. This was again vacuum filtered to remove the carbon, and as you can see, this step did a pretty good job of removing most of the residual discoloration. At this point, I simply set the flask back up for another short path distillation and quickly boiled away all of the ether. This time there was far better separation of the boiling points, and the moment all of the ether had boiled away, the temperature rapidly spiked to the boiling point of benzaldehyde. Given that benzaldehyde is a fairly delicate molecule, particularly when heated, I decided to cut the distillation here and accept a minor impurity rather than risk destroying the product I'd worked so hard for. As a little indication that maybe skipping the distillation really was a good idea, this receiving flask did catch a few drops of the benzaldehyde before I cut the heat. And as you can see, it quickly began to dimerize to benzoin, which formed long, thin crystals. I'm not really positive why this happened, but I've always had bad luck trying to distill this stuff. As a final cleanup step, I decided to pass the benzaldehyde through a 0.5 micron syringe filter into my final storage bottle to try and remove some of the slight haziness that was present in the flask. At this point, I was now finally done, and so I weighed my nearly pure benzaldehyde for a final mass of 41.83 grams, representing a 72.7% yield. While I am happy with this yield, it is about 20% lower than the literature maximum for this procedure. I'm almost certain I could increase this number by more careful temperature control during the reaction, as well as simply picking one method to clean up my crude product and then sticking with it. Since I don't really have proper equipment for any real analytical testing, the only method I could think of to confirm that what I've made here is truly benzaldehyde apart from boiling point and the distinct odor is density. Benzaldehyde has a density of right over 1 gram per milliliter, and as you can see here, the density of 25 milliliters is just over 25 grams. Apart from that, another way you can tell this is benzaldehyde is simply by looking at it here in the bottle. Benzaldehyde is strongly refractive, and it causes a slight rainbow effect at the bottom of the bottle that you really won't see with most other liquids. In any case, that's all I have for today. As I mentioned earlier, this video is only the first in a long series of videos I'll be putting out on some of the different things you can do with this incredibly versatile chemical. If you're interested in seeing those, feel free to subscribe. And as always, I want to give a big thank you to all of my members here on YouTube, as your support is vital in funding the work I do here. As a quick final note, I did want to apologize for the big gap in my uploads, as I've never really gone this long without releasing a video. I know most of you don't mind, which I really do appreciate, but I wanted to explain myself anyway. Basically, over the summer my schedule freed up a good bit, and so I decided to use the time to try and do some of the bigger projects that I don't normally have time for. The good news here is that I got a ton of really cool projects filmed that I'm super excited to release. But the downside is that I got very behind on the whole writing script and editing video side of things. It was a bit daunting even knowing where to start with the 8 terabytes of footage backlogged, but after a bit of thinking, I decided that benzaldehyde would be as good a place as any. With that, expect a lot more from me in the coming months, and I'll do my best to keep the uploads as consistent as possible. Thank you all so much for watching, and I'll see you next time.